Hello everyone. So in this session, we will talk about different quantization methods and how we can actually run those. So what we will be doing here is that we have multiple types of quantization methods. Okay. We have already talked about the types like GPTQ, GGUF, AWF, and we have seen why which one is preferred. So as you are all aware of that, what we will be doing is in this session, we will simply see how you can run them on your Jupyter notebook. Okay. And I'm doing this in Colab, and Colab is easy to use. So we are more normally using Colab because LLMs take a lot of space and need a lot of computation. So we are using the GPU of Google Colab. Okay. So for this one, we will use the Zephyr 7B. It is basically a fine-tuned variant of the Mistral 7 billion that was trained with the direct preference optimization technique. You can, if you want to know about this DPO, that is direct preference optimization technique, you can have a look at that. But you don't really need to know much about it, except for the fact that this this is basically a technique which is used to train large language models, for example GPT-3 or Jurassic 1 Jumbo, and this will basically allow it to better align with the human preferences. Okay, so unlike traditional methods based on reinforcement learning or other type of methods, this direct preference optimization takes a simpler and more efficient approach. So what happens here is that the large language models are usually trained on large amount of data, but this data does not always reflect human preferences. Now they may also generate creative text, and it might not be helpful and factual or aligned with the user intent. So what we do here in case of DPO is that the humans create pairs of outputs which will show the preferred and the dispreferred response for a given prompt. Now this can be done through simple comparisons. That is, there could be a person who could be choosing between two different type of summaries for a same article, right? So all this data preparation has been done manually or maybe assisted by the by some tool, by some AI tool. Okay, so this DPO basically analyzes these pairs and directly adjusts the LLM internally to the basically it adjusts the LLM's internal parameters so that it favors and generates the outputs closer to the preferred ones. Okay, so this approach is actually requiring less human effort and computational resource compared to the reinforcement learning. So because in reinforcement learning, the tool actually has to rank and do everything at their own, and all those things will be iteratively run, and for each and every response there will be a reward and you can say a negative response. So you will have it is a longer process basically. So this DPO is basically simple and more efficient. So that's all you need to know about the Zephyr. Now what we have is that for this LLMs which we will be loading here, so we will be looking at different LLMs, and we will be loading them in this notebook. Now, the suggested way is that after every load, you try your example, you try prompting it, and once you're done with it, you can try a lot more examples than what I will be showing. But once you're done with it, disconnect and delete the runtime, and then again connect with another LLM, because there are certain dependencies there are a lot of different dependencies in case of or your LLMs. So one LLM may not be compatible with the packages which are there for another one. So to be in a safer position, it's suggested that you restart your system. Basically you disconnect and then delete the runtime and then reconnect the GPU again. Okay, every time you want to connect to a different LLM. Okay, now to start with it, now if you want to delete anything, then I have given a piece of code here. Let me show you this one. Okay, this is the piece of code which you can use each time you are generating it. So let me add it here as well. We don't need it for the first time because we are just running it initially, so we don't need to run this. But if you have run this ran any LLM before in this particular notebook, then it's suggested that you do this first and then start and connect to another LLM. Now let us see the how we are going to do it. So we have first of all the main and the most straightforward and vanilla way to load your LLM is using the transformers. Okay, now Hugging Face has created a large suite of packages that allows us to do amazing things with these LLMs. So what we will do is we will start by installing Hugging Face, and from this here we have the pip install for Hugging Face. Okay, apart from that we have to install the accelerate, the bits and bytes, and transformers. Okay, so let's run this. Now obviously the pip install will take some time, but it will be still faster because we are using a GPU. Now after installation we can use this particular pipeline to easily load our LLM. So if you see here, we have this pipeline which we have created, and this contains this is a text generation pipeline, and the model which we are using is Hugging Face 4 Zypher 7 billion beta. Then this is the torch data type, and the device map. Basically if you're running on GPU or you're running in CPU, so device map auto will basically make sure that it automatically detects which device you're running your LLM on. So this is the simplest way of doing it. So I'll just run this as well. Now I am using this particular model. You could have opened and used any other Hugging Face model also. Okay, so here you can see different LLMs. So this is one of the LLM, that is Llama 2 13 billion chat. Then similarly, let me show you the block. So here you can see the block on Hugging Face. So basically the block is basically one of the LLM collectors. So this person has actually created a huge library of different LLMs. So you can have a look at different LLMs. You can see this is a German LLM. It is for German language. Similarly, there are around, you can see there are 3,863 different models, right? So you can select any of these. You'll have to do a little bit of reading, but mostly everything would be as I am suggesting you. So you can use that directly. So here we get, so this has already run. So now we have run this for Zypher 7 billion parameters. So basically this is the name of the model. Then we have the number of parameters. So 7b means 7 billion parameters and so on. So if you have 70 billion, that would be 70b. And beta is basically the version of it, right? So this is still downloading, and you can see it is downloading. This has completed. Now we can run this code, right? We can basically prompt this LLM. So how do we do that? So basically I'm creating a message. You can call it a prompt also. So this is, first we are suggesting the role. So role is of the system. So we are saying that the system is suggesting the assistant that you are a friendly chatbot, or you are a professional chatbot, or you are someone who are very friendly but talks like Shakespeare, right? So you will tell the role to the system here. Then we have the role of user. So basically what user is asking the assistant to do. So the user is asking, tell me a funny joke about LLM. Then we are running this, the pipe. Then we are tokenizing it and then apply chat template. And under this, we are passing the message and we are saying tokenize is equal to false and add generation prompt. Okay. So then we are getting the response for the prompt. This is the, we are basically getting the prompt. So this is our prompt. Now we need to get the response from our prompt. So for response, we are saying output is equal to pipe. Inside pipe, we are passing the prompt. We are passing max number of new tokens. We are saying if it should do sample or not, the temperature. So if the temperature is basically 0.1, then top P, basically the top, basically how much of the top answers should be considered to give out the response. We'll discuss about this. So this is 0.95 and then we are generating the response. So we just ran this. So here is the response. So why did the LLM go to the party? To impress everyone with its vocabulary. But unfortunately, it ended up getting lost in conversation and couldn't find its way back to its own thoughts. It spent the rest of the evening awkwardly nodding and repeating, and this is basically a joke. Okay, so this is a joke which our LLM is telling us. So this works fine. Now, next thing is pre-quantization. Now, basically what happens is that there is a really good way of quantizing your LLMs, right? We have already talked about it, that you can quantize your LLM and basically you will train your model, and once the model has been trained, we will be decreasing the quantization. Basically, we will perform quantization so that the size of each and every parameter value decreases, and this will basically allow us to have a smaller model which will take less computation, but will have a slight trade-off with the accuracy. Okay. And these models have already been created and generated and put in the block library which I just showed you, right? Now you can see here these are different models which are already created and placed in the model library by the block. Now, next we are talking about GPTQ. So, as we have already said about the GPTQ, so GPTQ is a post-training quantization. Okay, post-training quantization, you can obviously see that it will basically try to compress all the weights to a 4-bit quantization by minimizing the mean squared error of that weight, or you can say it will basically compress our model after the training has been done. So during the training it will be a full-fledged LLM, and after the training is completed it will just compress all the parameters. Now when the inference would be done, so during the time of inference it will basically dequantize the weights to a larger value, that is float 16, or for a better performance. Okay, so basically while handling the model you will get a smaller model, but for inferencing you will still be inferencing on a larger model, right? So what we will do, we will first have to delete all the variables which we have created and the model which we have already loaded. So I'll just run this so that we could delete that. Now, once the deletion is done, we will be using the transformers and we will be getting the model. Now, this time we will be getting the Zephyr 7 billion, again the same model but with GPTQ, right? That is post training quantization, right? So again, we got this model, we created a tokenizer, that is auto tokenizer from pre-trained. So basically it will tokenize my entire data which I will be passing into it using this particular model ID, the tokenization which has been used in this model ID, and use fast will basically fasten up the process for us. Then auto model for causal LM from pre-trained. So it will basically load this pre-trained model for us and it will again map the device automatically and it will pick the revised version, the main version of the model. Then we are creating the pipeline. So in pipeline, we are passing the model, the tokenizer and the task which is text generation. Now you can see that this is 4.16 GB file. Okay. The previous model was around a larger file. It was 1.89 GB plus 1.95 GB. These were different parts of the model. So you can see around 2 GB and that is 1, 2, 3, 4, 5, 6, 7, 8. So you can see about, or you can say 7, 14 and 15. So this was around 15 GB of model here. But this time we got only this 4 GB. So there's some error. So it is not able to allocate this. So what I will do is I will again restart this and then run the code here. So I'll just run this. So now you can see that the model has been loaded and I'm again running the same prompt. So this is the prompt which we have and this is the output which we needed. So we are just running for the output. So we have passed the same thing. So the pipeline remains the same which we created earlier. So if you see, this has created a new output. So why did the LLM go to the party? To show off its wit and charm, and of course, but unfortunately it got lost in the crowd and couldn't find its way back to its owner. So you can see it's still giving a good response. So now again we will run for GGUF. So for GGUF again you have to delete everything which you have loaded, all the model, all the tokenizer and the pipeline. And then we again use the auto model for causal LM and the transformer, and then we load the LLM and we use the GPU layers to specify how many layers will be offloaded to the GPU, right? So now we are using GGUF. Now, although GPTQ does compression very well, its focus is on GPU. And this can actually be disadvantage if you do not have the hardware to run on it, right? Now GGUF, which is basically a new version of GGML, is a quantization method that allows the user to use CPU to run an LLM, but also offload some of its layers to the GPU for a speed up. right? Now, although using the CPU is generally slower than using a GPU for inference, it is an incredible format for those running models on CPU or Apple devices. So if you want to run something on CPU or on Apple device, you can go ahead with GGUF, and still if you have that small GPU, if possible, then you can use that as well. Right now, especially since we are seeing smaller models and more capable models which are appearing, like the Mistral 7 billion, the GGUF format may also be staying, right? So we will be using GGUF now. So again, everything remains the same. We just load the Zephyr 7B GGUF format model. We give it the model file, then we tell it the model type, the GPU layers, and the tokenizer, we are giving it the tokenizer, the name of the model, and then we just created the pipeline for it. Now, once this pipeline runs, we again will run the prompt, and finally we will get the output from the pipeline by passing the prompt and the max new tokens to be generated, right? And the output format, if you want to see, I'll just show you the output format as well. So this is what the output looks like completely, and this will show you the output only. So let's just wait for everything to run, for it to load the model. You can see the model is 4.37 GB in size. So it will obviously take a slight amount of time to run. So once this running is completed, I'll show you the result. So here you can see the results. So this is the prompt. Tell me a funny joke about large language models. And this is the response which we got. Why did the LLM go to the party? To impress everyone with its vocabulary, but unfortunately it kept repeating the same joke over and over again, making everyone groan and roll their eyes. So this is what the output looks like. You can see this has the generated text, right? So this is what the output actually looks like, and this is when we print it. Now, next we will have a look at AWQ. Now we have talked about AWQ in detail. So AWQ again is basically activation aware weight quantization. It is basically a new format and is quantization method similar to GPTQ. Now, there are several differences between AWQ and GPTQ as methods, but the most important one is that AWQ assumes that not all weights are equally important for an LLM's performance. So, in other words, there is a small fraction of weights that will be skipped during the quantization, which helps with the quantization loss. As a result, the paper in which AWQ was written mentions that a significant speed up compared to GPTQ while keeping similar and sometimes even better performance. Okay, so basically in comparison to GPTQ, you will have a more speed and at least the same or even better performance in comparison to the GPTQ. Okay, now but the issue with AWQ is that it is still a little new and has not been adopted so much in comparison to GPTQ and GGUF. So if you want, you can maybe go towards GPTQ or select GGUF if you don't have GPUs. But if in case you have a AWQ version available, please use that. So we will follow the same thing, and again we will have to restart our environment, and then we will have to run the code. So I'll just show you the result and show you the code also. So for this one we will have to restart our environment and install the LLM. And from VLLM, we import LLM and sampling parameters. And in sampling parameters, we basically pass the mean parameters or the configurations which we usually have for LLMs. These are temperature, the top percentage, the max number of tokens. And then we create an object for LLM, and the model, we provide the AWQ version of the model. Say quantization again has to be AWQ, the data type, the GPU memory utilization, that is we want to go at max to the peak of 95% utilization of GPU, and max model length is 4096, that is the size which we wanted to have. Now we are giving the prompt, and for the prompt itself we ran the output, and in the output you can see this is the output to network, and here we just simply asked it to. So here you can see the model has been loaded. We gave a prompt, you are a friendly chatbot, tell me a funny joke about LLM, and this is the response that we have received. To network and expand its vocabulary. Why did the LLM model go to the party? To network and expand its vocabulary. Why did the LLM model blush? Because it overheard another model saying it was a little too wordy. Why did the LLM get kicked out of the library? Because it was being too loud and kept interrupting other models' conversations with its endless chatter. So you can see these are different jokes which it has generated. So you can use any of these models to actually generate responses for you, and you can use these for basically this course practicing the prompt engineering. Okay, thank you.